The two problems that I'm going to be doing today are rated 1100 and 1300. So for those who are trying to break Cyan, who break the barrier of solving the first three problems in a Div 2 contest, this video is for you. Hope you enjoy. Alright, so here's the first problem that we're going to do. I just spent a few minutes setting up the template of this problem. I haven't touched the problem at all. So I want to be simulating a environment that would be similar to if you were doing this in a contest. 3, 2, 1, go. Oh, well, all right, there we go. An equivalent way of saying this statement is that a number x is good if we can change x bits in the original string to make it a palindrome. That's just a fancier way of saying that. And the reason why is that XORing an element by 0 is not going to change it, whereas XORing a bit by 1 will change it. We have some conditions that we can meet. Either we can look at the palindrome in terms of pairs. So for example, the first and the last index are a pair because they have to be equal, and then the second first and the second last index are also a pair because those have to be equal, and so on. So for a pair, if the bits are already the same, we can either leave both of them alone or change both of them. So in other words, we can use either 0 or 2 moves to keep it a palindrome. Otherwise, if those two bits are different, we have to use at least one. And a little special case is that if n is odd, we can choose to either leave the middle index alone or change it, which uses up one move. We just have to do a little bit of casework. And I'll explain that casework as I implement the solution. How many of these pairs exist and whatever. So good pairs are pairs where initially both bits are equal, and bad pairs when both bits are not equal. And actually, I just realized that we only need to keep track of how many good pairs there are, because then we can just find how many bad pairs are given from how many good pairs there are. So good is incremented by 1 if the pair that we check is a good pair. And then bad is just going to be equal to the total number of pairs minus number of good pairs. And whether there's that middle index that can be flipped on or off at any time is only dependent on whether n is even or odd. So we can handle that as its own case. Tag is equal to 1 if it's possible to use exactly change number of bits to make the initial array a palindrome. Number of leftover changes is odd, then we have to use that middle index if it exists. And if it doesn't exist, then tag has to be set to 0. Alright, I caught my mic turning off for a bit. Hopefully it wasn't off for too long, but just to quickly summarize, I'm just iterating over all these changes and using a number of good and bad pairs to determine whether a value of x is good to use or not. Alright, still running on test 1. Okay, we passed it. So yeah, that was pretty straightforward, hopefully. And let's move on to the second problem. Alright, so the second problem of this video is actually going to be an interactive problem. And hopefully that'll be useful to you guys out there who might not be very comfortable solving interactive problems. So 3, 2, 1, go. Okay, so in other words, we have to ensure that we obtain the optimal answer if we're playing as Alice. So the first thing is to figure out what R is going to be for some initial set, because it wouldn't make sense to try to play optimally as Alice if we don't have an idea as to what the optimal set of moves are in the first place. Okay, so we can look at a sample interaction to help us out here. So this is the initial set. Alice adds 8, and then a smaller number gets removed. You add 57, a smaller number gets removed. We add 0 at the end, and then the end of the game maxes this. So Let's just pretend that we're Bob for a second. One way that we can always sabotage the mechs and keep it as small as we can is by removing small elements. Because even if because at any one point, if we're able to remove 0, we should remove 0, because then the mechs will become 0 after our removal. But the only issue with that is, if Alice adds the number 0 into the set, Bob can't make a move, and so that would be game over. We could just add 0 at the very beginning over here, and adding 0 will always end the game, because once we add 0, Bob can't remove anything else, because it's not possible to remove a number below 0. So the goal for Alice is to have the longest streak of consecutive numbers starting from 1, right before he adds 0 into the set. So the sample interaction is actually a little stupid, because you can just add 0 at the very beginning, and that'll end the game, and the mechs will still be 4. I wonder if it's always optimal if 0 doesn't exist. So for example, if we have 0, 1, 2, we can add 3, but then 0 gets removed, but then 0 gets added back, and then the game ends. So I wonder that we can, in this case, we can add in some arbitrary number, and then a number smaller than that gets deleted, but we can always repopulate that number. Any number that we choose at the beginning will be protected so long as the subsequent numbers that we add back into the set are smaller than it. So this gives me an idea. I want to first play around with a set. Let's say that the initial set of numbers are 1, 3, 4, 5. So let's say we add the number 2, then Bob removes the number 1, so we get 2, 3, 4, 5. But the thing is that if we add a 0 now, the max is only 1. And that's not necessarily a very high max. But if we try to add number 1 in right now, then max is going to be 0 because the game just ends, since 1 is the smallest number in the set. And we don't want that either. So we're going to have to add probably 6. But the issue is that once we add 6, Bob can remove any of these numbers over here. So let's say that Bob chooses to remove 2, and it'll be 3, 4, 5, 6. So at any one turn, Bob can make it increasingly harder and harder to achieve a better mechs. So in other words, we can't do much better than this initial state over here, because with 1, 3, 4, 5, if we just add a 0 at the very beginning and end the game, then the mechs is going to be equal to 2, which is going to be better than any result that we get by adding in a number that allows the game to still continue. Because then Bob can remove 1, and then it'll be harder to expand from there. So that's the case if 0 is already in the set. What if 0 is not in the set yet? So we can try to add the number, try to add number 3, then 2 gets removed, but that kind of like wastes a turn, because if we don't add a number that's the smallest in the set, then the smallest value will always increase if Bob plays optimally, and that will make the mechs harder to achieve. We can just add 0 and force the mechs to be 1 and just end the game immediately, because if we try to extend the game, then it'll make it worse for us as Alice to do that. 0, 1, 2, 3, 4, 5. Let's say we want to add a value into here. Let's say we want to add 6. But Bob removes a value, a strictly smaller value, so anything from 0 to 5. But here's the trick. Whatever value Bob removes from here, we can always just replace that as Alice in the very next turn. So if Bob removes 4, we can just add 4 back in as Alice. And when we add 4 back in as Alice, the range in which Bob can remove from will decrease, like this. So no matter what Bob can do, we can always replace that value immediately, and Bob's choice of moves will shrink all the way until he has to remove 0, and then we add 0 back in. And the set of numbers stays the same like this. So yeah, it basically means that if there is some set of numbers in the set that already lead from 0 up to x, then we can add in the value x plus 1, and then it will always be possible to maintain a max of x plus 2. Even if it's like only 0, 1, as like the numbers that we care about. Add in a 2, and then we can achieve a max of 3. And then even if it's just 0, we can add in 1, and then a max of 2 will be achieved. So we want to measure how long the streak is, because we want to measure a streak of this all the way into x. And the first move that we always make is going to be however long our streak is plus 1. And then this will just be the interaction phase over here. So I'm going to print out the current value, and then I'm going to read in Bob's feedback for my query. Current is going to be set as the number that was just removed. And yeah, let's go ahead and see if this works. I'm hoping it doesn't TLE because interactive problems can be quite slow in Java. Okay, it TLE'd. I feel like the solution is right. I would just have to go through the pain of converting this to C++. So I'll do that off screen, and I'll show you guys the results of that after I'm done. And that concludes the video. For the second problem, I did have to convert to C++, but once I did that, the solution ran perfectly. The logic that I explained in the thought process for the second problem is completely correct. So it shouldn't affect most of you who probably use C++ regardless. But yeah, that's pretty much the end of this video. I'll see you guys next time.